All right, pre-cal. Today we're going to be talking about exponential functions and the number e. Okay, so last time we were talking about exponential functions, and we saw a lot of y equals 3 to the x. I'm actually going to start off with y equals 2 to the x because I think it's a little more intuitive. So y equals 2 to the x is an exponential function for two reasons. One, uh, a is greater than 0, and two, a does not equal to 1, right? This is what we said the other day when we were talking about this, as we can see by this definition. So as we see here, let's see if I can blow this up a little bit. We can see that an exponential function with base a is defined for all real numbers x by f of x equals a to the x. F of x is the same thing as y, where a is greater than 0 and a doesn't equal to 1. So this is what we started off with last time. And we plotted some points and we kind of got an idea of what these graphs kind of look like. But today I want to look at it from a different perspective. So the first thing I want to do is I want to take a couple of points, and these points I'm going to take are going to be what we call in math discrete points. So what you can see that I'm doing is I'm taking uh, integer values of x. So 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, and I guess we'll do one more. Actually, no, that's fine. We can go with that. That's fine. Okay. And if I wanted to illustrate what this would look like, we know that this graph would look something, we plotted the amount to time in terms of specific values, it would look something like this, right? We can see that the first value of 2 is what happens after one iteration, right? We can see that the next value, which is 4, is what happens in the second iteration. And then in the third iteration, we can see we have 1, 2, 3, 4, 5, 6, 7, 8. Now, the way that this graph is color-coded is to show you, is to illustrate to you that after the first interval, right, you gain an additional 1, right? And that's this one in green. Then this green value, because it doubles, means that, or rather because we double yet again, these get doubled, but the blue gets doubled as well, right? And hence we have 4. And then we can see the repetition here again. So now we see we have 2, right? So 2 gets doubled into 2 more groups of 2, or 4, in the same way that the blue, that is 2, gets grouped into 2 more groups of 2, and we get 8. So another sort of representation of what we're saying. But what is actually going on here? So when we say y equals 2 to the x, this is one of the great tricks you can do in math. This is actually the same thing as saying y equals 1 plus 1 to the x, because 2 is 1 plus 1. Why do we want to write it this way? Well, what this illustrates is that what you're actually doing, this first one represents the original value. In other words, if you have the original value of 100% of the value, this second one represents the increase, right? So you grew at a rate of 100%, okay? And so that is precisely what doubling means. So if you double something, you increase it by 100%. So this is something that's kind of interesting, because if I wanted to make an argument, I know we're not talking about this version, but if we said, what does y equals 3 to the x mean? This means 1 plus 2 raised to the x, which means that the rate here is actually a 200% increase. So if you have a 200% increase, it's 3 times as much. If you have a 100% increase, you're doubling the value. It's twice as much. That's interesting in and of itself. So this is a great technique to know in math. We use this all the time, splitting numbers into sums that work. So 1 plus 1 is 2, and we use that. Okay. Now, why am I talking about this? Well, I want you to start thinking of it in this way because we can do more than this, right? So what we're really saying, especially with, let's say, let's go with a different color here. Let's go with this little light blue. What is this one saying, right? Well, what this one is saying is 1 plus 1 over 1 and raised to the x, right? And so why am I writing it like this? Because what we're doing here, right, is we're increasing this over each interval, right? So we're talking about an entire value of a rate. So what could transpire here is we don't have to necessarily cut this up into 100% each time, right? If our interval, we could say our interval, instead of being every single time, we could say that we're going to cut. Let's say that this is every year, right? Instead of saying from 0 to 1 year, we could say every 6 months or every half year, right? So what would happen is two things would happen here. One, our rate is still 100%, right? But we're going to have to divide this by 2, because what's going to end up happening in this scenario, right? We have to divide by 2 because we've cut the rate. If the rate is 100% every year, if we're doing every 6 months, we're doing half of that 100%, right? And also, if we're looking at this in the span of 2 years, sorry, 1 year, we're doing 2 intervals, right? We're doing 2, or you can think of this as 1 times 2, right? So what we're saying here is it's going to double, right, every half year. Now, I guess my first question is this an accurate representation of if we're cutting this up into 6 months, right? 100% in. So what, again, let me be clear here. What I'm saying is it is 100% of the value in 1 year, but we're cutting, instead of cutting it up every year, we want to cut it up every 6 months. So again, my question is this an accurate representation? And the answer to that is no. And the very easy reason why to see that that is a no is because we have to do half a year or it's 6 months, right? This has no representation of that half year or 6 months. So what would this graph actually look like? Well, we would maybe think that it would look something like this, right? And something like this, because what is going on here, right? Well, you have the initial year, right? But because we're now doing every half a year, so that's 50%, right? You have 50% more. Now, what's interesting here is if um, if we look at this now, right? If it's 50% more, then we're going to have 50% more of a 1, which now is 2. Let me draw this right. But there's something weird going on here, because this 50% should also have another value. So this, just like this one, this is incorrect. This too is incorrect, because you are doubling this 1%. This 1 does become 2, right? But moreover, this 50% is also doubling. So what does that become? Well, that's going to look something like this, right? Because what's happening is we took our original one, right? Which got doubled into being another one, right? But we also doubled the 50%, which became 25%. Okay, and you don't have to take my word for it, right? We can actually do this and calculate what it's going to be equal to, right? So what I'm arguing here is this visual representation is that it's 1 plus 1 plus 0.25. So if I add 0.25 plus 1 plus 1, I get 2.25, right? But let's see if that's actually true. Let's pull out a calculator and see what happens here. 1 second. Let me pull out a calculator. And let's see. Oh, let me pull it over here. Nope. I gotta make this smaller. So let's pull out a calculator here. And let's just type it in. Let's see what happens. So we have, I'm saying that it's the same thing as this. So that's going to be quantity 1 plus 1 divided by 2 raised to the 1 times 2. Look at that. It's the same thing, right? We didn't really need to do this on a calculator too, right? We could have just said 1 plus 1/2 is 3 over 2. And if you do 3 over 2 squared, you get 9 over 4, which is 2.25. So could have just done it like that as well. In any case, so what we see here, and this, what's interesting about this is that if I divide by 2, right? If I cut my rate, instead of doing just one interval, if I cut it every half, we actually end up getting more. Remember, when it was originally 1, right, we literally just plug 1 in here, you get 2, right? That's what this first graph is, right? This representation is what happens when you're cutting it up every month, right? Well, instead of cutting it up every month, cutting up a year into every 6 months, what if we cut a year, we divide a year into 3? What if we do it every 4 months, right? Well, what that would look like is something like this. So this is if we cut it up every 4 months, and every 4 months represents, right? We're saying 4 months because we're cutting a year into thirds. So 12 months in a year divided by 3 gives me 4 months, just to be clear, right? And so what are we saying? Well, what's going to happen is after 1 year, after every period, this one grows 33% more. And so what happens? Well, this 33, the one still grows 33% more, right? So if you're at 33, you tack on another 33, which gives you 66. But in addition, the 33% increases by 33%. So now that's 11%, right? So then what happens? Well, the 66% increases by 33%, which gives you 1. The 11% increases by 33%, which gives you 33. And then, the 66 increases by a third, which is 33. And then the 11% increases by 33%, which gives you 0.04. And so now when we add these up, we get 1 plus 1 plus 0.33 plus 0.04, which is going to give us what? That's 2.37. Okay. Again, don't take my word for it. If you want to, we can just plug it in. It's 1 plus 1 over 3 raised to the third. And this will be So this is 4/3 raised to the third, which is 4 to the third is 64, 3 to the third is 27. And so again, if I was to take the calculator out and do this, we would be getting 64 over 27, which is 2.37, which is what we more or less got here. Okay, so it's the same thing. Okay, so now here's the question. Well, instead of cutting this up into the year into thirds, we're seeing that every time we cut it up, when we cut it up into halves, we got 2.25. When we cut it up into the thirds, we got 2.37. Hey, look, it looks like we're gaining every time we cut it up, we're going to get more. So we can keep playing this game, right? We can keep cutting it up. In fact, instead of calculating each value, we can use a graphing utility like Desmos to do this. So I'm going to go ahead and do that. So we can see here, actually I put N, but I should really put X here. And so what we see, I guess it doesn't like what I put there. There we go. If we, now I don't really, I mean, we can look at the graph. I'm not really concerned with the graph. And I'm not really concerned with negative values. Let me just get rid of negative values. Actually, let me delete this whole thing. And so what we're concerned with, well, we did 1 earlier, right? And that was 2. Then we said 2, we got 2.25. Then we went to 3. And we can just keep increasing this, right? 4, 5, 6, 7. And look, it keeps going up. 8, 9, 10. Let's go bigger. 100, right? 1,000. So something interesting is happening. I ask you to consider what is going on here. We went from 2 to 2.25, which is 0.25 is significant increase. It's a big percent. We went to 3.7. It's not as much as a jump, but it's still a jump. Then to 4.4, it's a jump, but it's not as much. 44 to 48, it's a little bit more. 52 is roughly the same thing. It's roughly right. 44 to 48 is roughly, maybe you could argue 49, maybe 0.05. This is 0.04. All right, or 0.03. Then we went to 56 or 57, so it's the same thing. The 58 is 0.01. 59 is 0.01. We jumped to 70. That's a big jump. And then we went to 71 or 72. And we're at 72 here with a little more. And look here. Look at the jump. I went from 10 to 100, and this went up significantly from 9 to 10. But then afterwards, from 100 to 1,000, that's a lot of iterations. It went up 0.01, right? And just for dramatic purposes, what do I have? 4 zeros, so adding 1, 2, 3, 4, 5. So what this is illustrating, now I'm not proving this, I'm just kind of throwing in numbers to illustrate, is that this is getting closer and closer to a particular value, right? This is only a slight change. This value is E. Okay, this is what E is. E stands for Euler's constant. A mathematician, his name's Euler, and it's 2.718. So what we say in fancy math notation is, give me 1 second, I'm gonna pull this up. Actually, I'm gonna pull it up from here. In fancy math notation, this is this right here. This is what we say. So the limit as x approaches, you know what, I can do better. 1 second. Let me do better. This is the same thing as the limit as x approaches infinity of 1 plus 1 over x raised to the x. And this is what e is equal to. So the idea is, as we get closer to infinity, as these x values get bigger and bigger and bigger, we get, as we saw, it's getting closer and closer to this number called e. Okay. Why is this significant? Why go through this explanation of e? Well, e has tons of properties, and we use it for a lot of different reasons. But what I wanted to show you is that you're going to be playing with these formulas like compound interest, right? And what I want you to see is that if I use the example here of y equals 2 to the x, when we broke it down to 1 plus 1, right? This one and this one, what is the relationship between this and this? Again, what I'm asking here is, if I give you y equals 1 plus 1 to the x, this right here is the representation of this formula, right? So what we're saying is p is the initial value, which is 1, right? What's the number in front of the parentheses is 1. R over n, remember we said we could divide 1 into 1 over 1, and then this is where we started changing this. We said we're cutting 100% up. We're cutting it in half. We're cutting it in thirds. We're cutting it in fourths, and we kept going on and on and on. So n, and look at this. What does n represent? The number of times the compounded per year. So how much we cut it up, right? This t is the number of years, and n is the number of times compounded per year. So what that means is, if you multiply n times t, what does n times t give you? It gives you the amount of iterations that you did this. That's what x is. It's the iterations of doing this. So how many times am I multiplying this, whatever's in the parentheses, over and over and over again, right? So this is why earlier we said, when we first did it, we divided by 2. We said 1 times 2, right? Because we did this twice, right? And then over here, we did it 3 times. That's why you're saying 3. We cut it up into thirds, and then we multiplied by 3 because we did 3 iterations of this 1/3, right? And that's where that's coming from. So if you understood what we discussed here, that is this formula right here, right? And then the cool thing, I think this is amazing, which is you have this other version, which is called compound continuously, which is this equation. And what's really cool here is that E, we just said E represents what? Well, E is this, right? So when this formula approaches infinity, if you cut up the intervals, instead of 1, 2, 3, instead of discrete values, you turn into a continuous value, it becomes E. So this formula right here is actually this formula as n goes to infinity. Okay, and there's a little bit of fuzziness here, because I would have to go into depth as to what r times t is and how that's related to it, but it's pretty much the same. It's the same. There's a little fuzziness here, but it's pretty much the same idea as what this is. Okay, so it's kind of cool. This formula right here is the byproduct of what we were talking about, right? And then if we do continuously, well, that makes sense, because if you cut something up continuously, the value has to approach E, as we showed through our Desmos and as this approaches infinity. Okay, so these are the formulas we're gonna play with in terms of solving these problems. Now we have to talk about a couple more things before we move on. In order to solve some of these problems, we're going to have to use what we call logs. Okay. Now, there's 2 types of logs that we want to talk about. The first is if you see a situation like log let's say log base. Well, first off, if you just see log of some value, like let's say log of 100, okay, what you need to understand is that what's implied is that there's a base here of 10. So if there's no number written, it's base 10. In other words, log base 10 of 100 is the same thing as saying log 100. So what is this all equal to? Well, this is actually all equal to 2. How come? What all a log is saying is when you write 100 with a base of 10, what is the exponent? Well, 100 is 10 squared. So when 100 is written with a base of 10, what is the exponent? The exponent is 2. Okay? That's what a log means. Now, sometimes you're also going to see something called the natural log. Okay? The natural log is represented as ln. And so if I give you something that is ln x, all this means is log base e to the x. So if I give you, for example, the natural log of e, this means it's log base e to the 1, right? E is e to the 1. So if that's true, then what is this equal to? This is just equal to 1. Okay, so we need these properties in order to solve the problems we're going to deal with. And so now let's deal with some of these problems.